It may very well be the case that if we look at the nature of our work, we'll discover that initially when we're doing analysis, our role is to just write functions, or to use functions, that is. So we call f, we call g, we call f, we call h. We're just using functions that are provided to us. And as our role becomes more senior, our contribution becomes more abstract. And so we start off just by using individual functions that somebody else wrote in order to answer a question. And then we say, oh, you know what? It's better for me to help the people answering the questions to answer the questions. So I'm going to package these up. I'm going to find patterns, and I'm going to write functions. I'll write function 0 that calls these functions in some order. I'll write function 1 that calls these functions and connects their inputs and outputs in some particular fashion. Well, it turns out that as our work becomes more abstract, and as we move from our primary activity being the use of functions to the writing of functions, this is exactly where decorators come up. Let's talk a little bit about the decorator syntax. The @ syntax in Python really doesn't mean much of interest. All it means is whatever this function created, whatever entity was created by this def definition, will be passed to the callable dec, and the name will be rebound. That's all it means. When you look at things like higher order decorators, you start scratching your head trying to figure out how do they actually work, what's really going on, come back to this correspondence, because this is the answer to every question you might have. If you see somebody writing some crazy decorator that looks like this, a higher order decorator, then think all they're doing is this here. And then you can break it down and say, okay, there's something that takes some arguments, and what it returns is then passed f, and then what that returns is then rebound to the name f. And that's all there is. In fact, I often say that decorators aren't a very interesting thing in Python. What's really interesting is dynamically creating functions at runtime, closures, and some of these other mechanics. Here, it is really a little bit more than a syntactical transformation, which means that higher order decorators, or things that return decorators, are again not all that interesting. It's just one more mechanical step. It's one thing that leads to another thing that eventually leads to the rebinding of a name for something that's been defined with a def. This is, in fact, the key mechanic that is necessary to understanding decorators. Let me show you a canonical example of how this may play out in practice, though. Let's say we have some framework, and in that framework, we have some code that is fast and we have some code that is slow. And we need to perform some instrumentation. It's often the case that we'll see decorators pop up in instrumentation tasks, trying to identify how long something takes, how fast something is. Now, these functions are very appropriately named. Fast is fast and slow is slow, but we don't really know that without measuring that. Maybe the names might be misleading. And so we'll think, how do we time these? Well, naively, the first thing we might do is we might wrap every invocation to fast or slow with a perf counter and some printing of the output. Well, this is not particularly desirable. The reason for that is I can barely see the original fast and slow code. I am so overwhelmed by instrumentation code here. This is extraordinarily disruptive. I can barely see that on this line here I did what was actual work. On this line here it was actual work. On this line here it was actual work. On this line here it was actual work. And the rest is just instrumentation noise. In fact, you may not even notice that there is an error here. I have incorrectly done this instrumentation. Here I have failed to add another after line to one of these, and as a consequence, I'm getting bad instrumentation. I couldn't even tell that my instrumentation was bad. Also, the output's not that great. I'm interleaving the actual program output with my instrumentation output, which, yeah, I guess I could send one to the standard out and one to the standard error, but likely I want to collect all that instrumentation output until the very end. And furthermore, if I want to turn this off, it is very, very disruptive for me to turn this off. I have to comment out all of these lines, and I have to make sure I comment all of these lines out. And some of you may have noticed that I just now accidentally commented out some good code while trying to comment out my noisy instrumentation code. So across many different axes, this is just not a great way for me to do instrumentation past. Maybe the simplest, just tell me how fast one line of code takes. Well, I can improve some of these in some ways. For example, I could use the debug variable that is introduced in our global scope that's set by our Python interpreter to true unless we pass the -O flag. And I can turn off the instrumentation pretty easily, at least from the outside. I could say run this with Python -O, and then the instrumentation is turned off. So I guess that's kind of useful, but all the noisiness of the code remains. I wonder if there's a way I can remove that noisiness. Well, it stands to reason that this is probably some kind of intentional repetition. The reason that I say that is it's likely the case that if I did this line of code, I must always do this line of code afterwards. And so there's some connection between these two. It also stands to reason that if I'm going to print them out in one fashion, like with a certain number of digits of precision, I probably want to print out all of the instrumentation lines with the same number of digits of precision. And so as a consequence, it seems like my answer here is to write a function. Well, I can write a function. What I could do is I could dynamically determine whether the before and after should be the instrumentation code or just simple no ops. And here in my instrumentation code, I could say, okay, capture the before and then capture the after. Although it's a little bit clumsy because I have to capture this in a global scope, because otherwise how does the after have the ability to access what happened before? And the code is a little bit less noisy, but some of the errors remain and the printing of this still remains. And so maybe I can do a little bit better. What I could do is I could think a bit further than that, and I could say, you know what? What if I dynamically pass this function in? I say pass in this function as though it's any other data, dynamically define that as either a no-op or passing it in like this. And then here, I can leave my original code as being mostly unchanged from what it was without the instrumentation. This is what it would look like without the instrumentation. And this is what it looks like with the instrumentation. Slightly disruptive, but not that disruptive. The printing is still happening in places I don't want, but here I can make use of functions being data like any other, and I can just pass in that function to something that captures my before time, my after time, and calls the function in the middle. But what if I were to, instead of calling this here, I were to define this function? What if I were to dynamically define this function? What I'm going to do is I'm going to pass my function in, and I'm going to dynamically define a new function that includes the original function behavior with this wrapped before and after instrumentation. In which case, now turning this on and off is as simple as not calling timed. And in fact, what I could do is at the top of my program, I could say, you know what? I don't actually need the other branch of that debug logic. If I'm in debug mode, I'll just swap out the original function with its replacement. If I'm not, I'll just leave it intact. In which case, my original code looks like exactly like the instrumented code. And a matter of turning this on and off, I can toggle that with my -o capital O flag, or alternatively, I can just not apply this additional wrapping by commenting out this line. And here, if I were to break these lines apart so that they are sitting a little bit closer to the function definition, well, I can see I defined something with def. I took that name, I passed it to some callable, and I rebound the name. This is exactly our decorator pattern. And so I could use a decorator to perform this syntactical transformation. And here you can see a decorator. Now, could I make this even better? Could I improve some of the problems with the printing of this? Well, absolutely. And in fact, it turns out that decorators are the solution to many problems of improving this instrumentation. For example, what if it were the case that I wanted to provide an ability to, in one or two places, turn off this instrumentation? Well, what I could do in this decorator is I could give you the ability to access the original function. And then here we can say, okay, use the original function, but the other ones are instrumented. Additionally, if I were to take a look at the help text for these functions, I'll see that this reflects my brand new dynamically created function, which isn't that great. So if I'm going to be assigning attributes on this function, I might as well assign attributes such as overwriting the name. And if I'm going to overwrite the name, let me overwrite the docstring in case there is one as well. And let me do the same thing to the signature. Well, here you can see an interesting pattern. The decorator was really a pattern where every time I defined a function, I did something associated with the definition of that function. I replaced it with its instrumented version. Here, every time I define this inner, every time I happen to write one of these decorators, I do something in common. Well, maybe there's another decorator I can use. And in fact, here, you can see an example where I have a higher order decorator with the use of the functools.wraps higher order decorator. Here we have a much more sophisticated example. We have our original code, which is largely unchanged. We allow it to be decorated with something that times things, that's given a variable, mutable variable, a list here, or maybe a collections.dec with a maximum length. This code here is the equivalent of saying this. So you can think whatever this gives us is going to be the decorator that we just have what we had before. Well, what this is going to do is in its closure, it's going to capture a reference to my telemetry. And then in the original decorator, I'm just going to append to that telemetry, and I'm going to append some rich object that I can operate on. And so this gives me the ability to actually process the telemetry after the fact. So I can print these out in nicer order, and I can even turn off this decoration. I can even turn off this instrumentation as I see fit by doing that .orig. In fact, I can take this example and I can make it even more complicated. You can see many of the additional details here are really implemented using this decorator mechanism. Here, I'm going to say that this is an instrumented function. And to be an instrumented function means that when you're called, you call that function within some specified context manager. And you can set that context manager via a function on this replaced function, which then allows me to, not at my library level, but at my ad hoc level inside my script, to define some mechanism for collecting that telemetry, and here in this case doing some nice printing of that mechanism, but collecting that telemetry, maybe even collecting some additional information in that telemetry like the line number where the line was called, and to even allowing myself to use a context manager to say anything under this block that is the fast function is going to now be called with this context manager. The slow function will be called with this context manager, and it'll write to this telemetry. So you can see a very sophisticated example making use of all of these things where we can even denote, oh, these two functions that were inside this context manager were decorated or were called via this mechanism, via this instrumentation mechanism. And I can have ad hoc mechanisms. I can extend these mechanisms as I see fit. I no longer have to have too much of the stuff predetermined in the library level. And many of the mechanisms here make use of that decorator pattern. Decorator itself, syntactically, not that interesting, but the things that we can do with it, very interesting. And most of these rely on just acknowledging that Python functions are created at runtime. When they're created, they can close over their environment, so they can capture references to things that were in their enclosing environment. And Python functions are data like any other and can be put into data structures, data types, can be passed to functions, returned from functions like any other.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.